This video is going to cover the shear and moment diagrams for beams. So here we have a beam. It's a pin and a roller support, a roller at A and a pin at B, and we have a linearly distributed load of 7.5 kilonewtons per meter going across this whole beam. We want to draw the shear and moment diagrams for this. So to start with, we kind of need to find our reaction forces, AY, BY, and technically BX, though BX is not really going to be present. So to start with, we're going to sum the forces in the x direction, set it equal to 0, and we'll find that BX is equal to 0, yay. Then we're going to sum the moments about either A or B. I'm going to pick B because of my linearly distributed load here. So I'm going to take counterclockwise to be positive and set it equal to 0. So I do have AY going up. AY going up is going to create a negative moment for me. So minus AY times the perpendicular distance of AY to B, which is 3 meters. Then we have this linearly distributed load. He's going to be going around this way for B. So he's going to be positive. So we have plus. We need his resultant force, which is going to act about right here, which is going to be 1/3 of the distance of 6 total. So that's that distance right there. So his resultant force is again going to be 1/2 times the base of 6 times the height of 7.5. And again, we want his distance over. So all of that together is 1/2 the base times the height for the resultant force times his distance of 1/3 times 6. So we get that AY is equal to 15 kilonewtons. And lastly, if we sum the forces in the y direction and set it equal to 0, we got AY going up. We have this minus this resultant force, which is 1/2 the base of 6, the height of 7.5. And then we have plus BY also, so BY is going to be equal to 7.5 kilonewtons. So now that we have those, we can write those in. AY we said was 15, BY we just said was 7.5, and BX we really don't care about. So we have our full loading diagram. Now we need to start drawing our shear diagram. Now this isn't very fun because it's already a 1 degree here for the loading. So that's going to, as we integrate, we're going to get a 2nd degree. So this is going to be rather fun. But we're going to start at 0, right? There's nothing over at this end over here, and we start going down. We're going to start going down until we hit right here. We need this area under the loading diagram. So this area, in order to find this area, we need this height, and we're going to use some similar triangles here. If the total distance is 6 horizontally, and that gives a height of 7.5, then if the distance is 3, then that's going to give us literally half of 7.5 is going to be our height there. So this area, area 1 is equal to 1/2 the base of 3, the height of 1/2 of 7.5. That's going to give us an area of 5.63. So we need to be going down, but we're starting off really small. We're finishing really big. So we're going to start off with the slope really small, and down here we're going to be at negative 5.63, and he's finishing really big. So there's our 2 slopes, and we just got to connect the dots. And again, this is going to be a 2nd degree because our loading was already a 1 degree. Then we have AY. AY shooting us straight up 15. So from 5.63, we got to go up 15, so it's going to put us up here at 15 minus 5.63, that's 9.37. Right, so we go straight up 9.37. Then we've got to come back down again. So now we're going to try and break this guy up into two parts. Since we need to find the area of this, we're going to break it up into this area. We're going to call this A2. And A2 is going to be equal to, it's a rectangle, so the base is 3. The height is the same height over here, so half of 7.5. That's A2, so that's going to equal 11.3. Then we've also got this area of the triangle over here. We're going to call this guy A3. So A3 is going to be equal to 1/2. The base is 3. The height of this triangle is 7.5 minus half of 7.5. So again, half of 7.5. So area 3 is going to give us 5.63. So in total, area 2 plus area 3, this is going to be 16.9. So from our 9.73, we need to go down 16.9. So that's going to put us down here at negative 7.5. And again, we're starting off small, getting to really big. I mean, it's not small, but it's smaller, getting really big. So small slope, getting to really big slope. That's the direction we're going. And again, this is a parabolic as well. Now that we're at negative 7.5, don't forget we got to shoot back up 7.5, so that puts us back at 0. So our shear diagram looks absolutely so wonderful. And remember that the area under the curve for the shear diagram is going to be the moment diagram. Well, that's fantastic, except we kind of need the distance to this point, either from the right or the left, right? We know that this distance is 3 meters, and we know the full distance over here is 3 meters, but I need to know one of those two distances. So how do you find it? That's a really good question. Well, what we know is that our shear is equal to 0 at this spot. So if I had, say, my shear equation in terms of x, and I set shear equal to 0, where it equals 0, that would give me what x was. So I'm going to do just that. I'm going to draw myself a little, let's say off to the side here. We're gonna draw ourselves a little free body diagram sketch of some internal loading. Now, when you cut into this wonderful member, don't forget we've got our 15 for AY in here, and we said that's 3 meters. And the overall, we don't know what the overall is, but he's X. And we've got our internal shear. Got shear here, and we want to know what is the value of W here. Well, this is effectively, it's similar triangles, or it can also just be the slope of the line. The slope of the line is equal to the rise, which the full rise or height is 7.5 over the run, and the full run is 6. And this is times x for the slope. Or if you really want, you can draw out similar triangles and it works the exact same. So there's our W. So now we want to find our shear equation. So we need to sum the forces in the y direction and set it equal to 0. We got 15 going up, we got shear going down, and we've also got this force going down. So this force is a triangle. So it's 1/2 the base of x, the height, 7.5 over 6 times x. That's quite fun. So our shear equation is equal to 15 minus 7.5 over 12 x squared. So again, we want to know where shear equals 0, what does x equal? So our equation is 15 minus 7.5 over 12 times x squared. Move the 15 to the other side, multiply by our negative 12, divide by our 7.5, take the square root. We're going to get that x is equal to 4.90 meters. So again, x is being measured from this side over. That's where x is. So if I want to find, say, this spot right here, this would be the total distance of 6 minus 4.9, which is 1.1 meters. And the reason I'm going to do this is because I want to take the area of my little dude here. I'm going to take the area of this guy. So the area of this guy is, funny enough, it's a really similar equation to the triangle equation. So a triangle is 1/2 the base times the height. Well, a parabolic, triangle being a 1 degree slope, 2 degree slope here is going to be an additional number on the bottom. So instead of 1/2, it's 1/3 the base, which I just found of 1.1 meters times the height. The height down here is negative 7.5. So my area for here is going to equal negative 2.75. And then again, because I enjoy the simple equation for this instead, I'm going to find area of this guy, which again, he's the same shape. He's not the fat part, he's the skinnier part, the part that's on the other side. So again, this is 1/3 the base of 3, the height of negative 5.63. All the 3's cancel, we get negative 5.63 for the area. So we found the areas, and again, we're going to do some cool magic here. We need to turn that to our moment diagram. So again, we start at 0, and we've got to, it's negative, so we're going to go down to negative 5.63 because that's the area there. We're starting at 0, we're going to go down to negative 5.63. Now, because this was a 2 degree slope, we're going to have a 3 degree. And it's going to work the same. We're starting off pretty small here, getting pretty large there. So starting off pretty small here, getting pretty large over here. And that's a 3 degree. Looks effectively the exact same, if you draw it correctly. Then we're going, this big area, this big area right here. Well, I don't want to calculate that. To be honest, I just really don't want to calculate that. That's a nightmare. So I'm going to start from the other direction. So if my other direction, I have to go down 7.5 to hit the end. Then I'm going to end at 0. I got to go down 2.75. That means I'm actually going to start at 2.75. Right? Since this last area is negative, I need to be going downward, so I'm going downward. What shape should it be? This is starting off pretty small, and this is pretty large. So I'm going to start off pretty small slope, ending pretty large slope. So there he is. Again, don't forget this is a 3rd degree. And whatever this magic is, we're ending small, we're starting large. So we're starting large, ending small. Ta-da. And I don't need to find the value because I already did. It's 2.75. So again, this is a 3rd degree, and there is my moment diagram. So my shear diagram just did get a little bit disgusting there, but there are my shear and moment diagrams for a not very fun beam.